Hey friends, welcome to our channel. Let's look at today's daily challenge problem, minimum cost walk in weighted graph. This problem is marked as hard, and however, it's a typical graph traversal problem, or you can understand it as disjoint union or union find method. So here, let me first see what we are going to do. So here, what we are going to do is the method we are going to use disjoint set. So or you can see it's union find method. So this is the one thing. Another ingredient is the properties of bitwise add. So with these two ingredients or methods and properties, so we can address this problem in a very elegant way. So here basically we are given a number of nodes, right, and then edges, weighted edges, and we have a query. So given each query, so we want to see what's the minimum cost of walking between these two nodes. First, if these two nodes are not in the same connected component, so the cost would be -1. Otherwise, we want to make it minimized. So for example here, right, 0 and 3 are in the same connected component. So here the corresponding output is 1. With that said, we can also look at example 2. So if you look at 1 and 2, right? So here the output would be 0. So actually you can see how we get 0, right? But I want to postpone a little bit. And first I'm going to explain the property of bitwise add for positive integers. So first is that if you have two numbers, right, a and b, then it's going to be less than or equal to minimum of a and b, right? So this is very easy to notice because this is a direct consequence of this rule. 1 and 1, you are going to get 1. And 1 and 0 equals 0. And 1 equals 0, right? So the more number you are going to bitwise add with, then the overall smaller the number the result is. And another thing is that a and a equals a, right? So there's nothing to explain. Therefore, we just need to use as many edges as possible, but we only need to consider it once because this property, right? So for example, here in example 2, 1 and 2. So because they are in the same connected component, we can use all the edges. Therefore, the cost. So in example 2, the cost between the 1 and 2 is nothing but exclusive all of 1 and 6 and 7 and 15. So you can do this computation exclusive, do it all. But you can, if you see this should be less than or equal than 1, right? But also, and notice that 6 is even, right? In other words, the least significant bit is 0. So 0 add this 1 will be 0. So overall, we can conclude cost 1, 2 is 0. So this is actually my reasoning. So if you look at example 1, so if you look at the cost between 0 and 3, so let's say 0 cost 0 and 3. They are also in the same connected component. Then we can use 1 and 7 and 7, right? We know this result will be less than or equal to 1, but notice that both the two 7s, actually the least significant bit is 1. So 1 and 1 and 1, you are going to get 1. That's why you have 1 for this, right? So with that said, actually we are ready to code the problem. So the coding plan would be the following. Get the connected components, right? So here we even don't need to get the connected component. We just need to get the the representation of that connected component and the corresponding result, right? So we don't need the specific connected component. You just need to know the final number, right? Like anything in this, any two nodes in this number will correspond to 1, right? Any two nodes in this will correspond to 0, right? So final number corresponding to each connected component. Let me use CC. Right, so this is the one. And so for this, how do we do this? So we can use two options. So graph traversal. So you can use BFS or DFS and union find, right? So here I'm going to use this one. Use this because it's very natural. So with that said, let's do the coding. So here, first let me define two dictionaries. One is called roots. So originally, for each node, the root will be itself. Then regs. So here I originally is 1, just itself for I in range M. So notice that these two dictionaries, so these two variables are mutable. So this is important for us. So next we are going to write two methods. One is called find method. For each node we want to find its root. So this is the one. Another one is define a union, right? So given two nodes, so we want to join the two clusters where each I and j are in. So then also we want to get a get clusters. So given edges, right? So we get the dictionary, and then the dictionary will contain. So for each representation of the name of the cluster, the corresponding number, right? So here I write the logic here. So our coding structure will be like this. So once you have that three functions, what do you do? So basically, first you are going to iterate over edges, right? So here we know it's weighted, but in the first pass, when we do the union, we don't need the weight, so we just have union ij. So once we get this union ij, so we can get the d. So let's get clusters, right? So edges. So in this case, we use the full information, and then we are going to initialize a result. So basically, we iterate for ij in query, and then we get the roots. So roots are root I, root j as find I and find j, right? If they are not the same, meaning that they are not connected, so you just need to append -1. Otherwise, you are going to append d, say root I or root j, because they are the same. Then we just need to return this answer. So this part are the problem logic. So this part and the find and union is the union find logic. So here get cluster also taking some consideration of the problem logic here, because typically you need to get the clusters, but here I just need to get the number. So with that said, let's first do this. So here I'm going to do find with path compression. So this actually is not absolutely needed, but I want to expose more information. So here I'm going to initialize a result variable, and then we're going to iterate. We use a while loop. So while result does not equal to roots result, then we are going to set the result to be roots of this result, and then chain up, right? Then just return result. Because if you exit this while loop, then roots and result roots of the result will be the same as the result itself. But here I want to add one more line. So basically I apply roots to both sides. So this corresponds to set the roots of result to be the roots of the roots of result, right? So this is the so-called path compression. So this is just one way to implement this, right? So this finishes the implementation of find. Now let's look at the union method. So because we have already implemented the find, we can first find root I, root j. Find I, find j. Then here, let me mention that I'm going to do union by rex. So this is also not absolutely necessary in this problem, but again, we want to expose more information. So here, if root I equals root j, so we don't need to do anything because they're already in the same cluster. Otherwise, if they're not the same, then we'll check the rex. So rex, if root I has a larger or equal rec than that of root j. So we are going to set the root of root j to be root I. And then correspondingly, we combine the cluster. This corresponds to increment the rec of the root I. In other words, the cluster represented by root I increment by this size or this rec. Otherwise, we do the reverse, right? Let's copy these two lines. And then we are going to set, because root j represents a larger cluster. So we set the root of root I to be root j. And then the size of root j is incremented by that of root I. So this finished the implementation of the union. So now let's look at the get clusters. So first, we are going to iterate, right, for I, j, and w in edges. So first, we are going to find, let's say root I, root j as find I, find j. So if root I does not equal to root j, so we don't, they are belonging to different clusters, we do nothing. And then if they are the same, so then what we can do is this. So if root I not in D yet, then we are going to use root I as the representation of the cluster or connected component containing this root, or you can also say containing I. So this would be W. Otherwise, then we are going to not exclusive, bitwise add with respect to W. So that's the main logic. So these two lines actually encode all those requirements, the minimum cost of work. So with that said, I guess that's it, because we have already written the problem logic. We can now test it. Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes the generic cases very fast. So now let me make some comments. The first comment is that we encode the minimum cost of a walk into the get cluster function. So this is, largely due to the properties of if bitwise add. So this is the one. Another one is that here we used a disjoint set, or you can see union find method. The extension is, can you try using graph traversal to get connected components This is the second one. The third one would be here I'm writing disjoint set. Here writing two functions. So can you implement this by disjoint set data structure? So in other words, you write a class, right? Let's say call it DSU, and then you do some initializations, all right, self, or you can add something, right? So then you also implement say find method and then you also implement union method self ig, right? Or if you like, you can also implement get clusters, but you can also put it in problem logic, right? It does not matter. So this actually just then still, if you write DSU, there are two possibilities. One is write the racks and roots fixed. For example, here I can write self rack to be say 1 times an n, right? Self roots just I for I in range n. Or you can use a dictionary, and then this way you write it fixed because a priori we know there are n nodes. So this is one. Another one is dynamically determine dynamically determine the roots and racks. So this is also important, but in this case you can, let's say, use dictionary, or you can just write like this. Then when you write the find function and the union function, you need to check if the key is in the dictionary represented by racks or roots. That's also another possibilities. In principle, if you know this, given n, yeah, you can write a good solution. But actually, it would be great if you can also master this too, right? Writing a class and then still two possibilities. Yeah. So this is the third comment. So with that said, I guess let me say the last one, right? So we have a playlist for a union find in our channel. I guess it contains more than 20 problems. So you can practice that. I guess if you can practice all of those, so you will find patterns and you'll be very familiar with those kind of problems. So with that said, I guess that's it for the current video. Thank you for watching.